The topic of this lesson is something called the photoelectric effect. I know we're near the end of the quadmester and people are starting to feel a little bit burnt out and motivation is sliding a little bit. But when I talk to people when they come back and visit, this is a topic that's done in first year physics courses in different programs, so it might be worth putting a little bit of effort into it. What the photoelectric effect is it's basically a way to detect light. When light hits a metal, as long as that light has enough energy, an electron is ejected from that piece of metal. They're just regular electrons, but when you read about it, sometimes people call them photoelectrons because they're electrons liberated by the light. Those ejected electrons, they have kinetic energy. If the incoming light has more energy, then those ejected electrons will have more kinetic energy. So the more energy you put in, the more energy those kinetic energy those electrons get out. It's a cool little effect, and it's used in a few places that you're familiar with. To save batteries in your cell phones, it's smart to dim the screen when the phone is in a room that isn't very bright. So let's say you go into a movie theater, you're not supposed to have your phone on, but in the movie theater, if the room isn't very bright, then this ambient sensor kind of pays attention to the light, and when it notices the room isn't very bright, it dims your screen, because by dimming the screen, that'll save your phone's battery. Those sensors in your phones are based off of this photoelectric effect. Similarly, if you've got a garage door opener, those little gate things that keep track of whether something's in front of the door or not, on one side there's like a infrared, I believe, beam being shot across. On the other side, there's one of these photoelectric detectors. If the detector over here senses the beam, then it knows that the doorway is clear. But if this detector over here doesn't sense the beam, it presumes something's in the way. So the logic is if the beam is blocked, then the circuitry tells the garage door, to stop putting the door down. Also based on the photoelectric effect. So it's kind of cool. Depending where you head, maybe engineering stuff, you'll engineer something that needs a light detector. You may use something along the lines of this photoelectric effect. All right, here's how we're going to use the photoelectric effect. We'll talk more about it in the next lesson. But this German physicist named Planck, spelled Planck, pronounced Planck, he was a big deal. He was sort of like almost another Einstein, a really clever physicist. He was doing some work to figure out a problem that we'll talk about later, and he came up with this rather simple equation that the energy of light is equal to a constant multiplied by the frequency of light. H is a constant. They name it Planck's constant now. F is the frequency of light. This is the equation he came up with, but from grade 11 we know that V is equal to F lambda. So if we're talking about light, instead of V we can say C is equal to F lambda, or if we flip-flop things around, F is equal to C over lambda. Usually when we talk about light, we talk about wavelength. So another version of Planck's equation is E equals hc over lambda. It's the same equation, energy equals a constant multiplied by C over lambda. C over lambda is just mathematically equal to the frequency. This is a really cool, simple equation. Pause this video and you can see me using it to solve a question. However, this cool little equation is a huge conflict with what we talked about in last unit, the unit we just finished on wave optics. In the wave optics unit, we said light was a wave. That's the only explanation, one of the multiple choices I tend to assign. We know that light is a wave because wave properties are the only way to explain interference. And we did a lab on interference. You didn't get to actually use the equipment, but you'll have to trust me that we used real equipment. It wasn't some sort of weird trickery. Light does interfere. That means light is a wave, and in the wave perspective of light, energy is related to amplitude. But this Planck guy's come along and says that no, energy is not related to amplitude, energy is related to frequency, or wavelength, or color. These are in complete conflict. They both can't be right. Either light is like a wave like we talked about in Unit 4 and energy is related to amplitude, or light is whatever Planck is telling us and energy is related to frequency, wavelength, or color. To figure out which is correct, we do have a lab to do it. In science, when we have two models that are disagreeing, the best way to figure out which model is right is to find a practical lab, like something we can observe, some real world observations, because the real world always tells us the truth. We can't really theoretically argue these two. We'll never come up with a full answer unless we do an experiment. We have to follow the data, follow the real world. So if our two models is energy related to amplitude or is energy related to frequency, we need a lab to do it. Because we're working remotely, and even if we weren't, the actual lab to do this one is crazy tricky to do. I've tried to pull it off in school and it's so finicky. We usually demo it if we do it at all. Photoelectric effect is tricky because it's all about light. So you have to do this experiment completely in the dark. So shut off the classroom lights and even put like a shield over the equipment so any light doesn't leak in. It's about ejected electrons, but electrons are crazy, crazy tiny. So there's a really, really small amount of electricity that's ejected. So we have to have sensitive equipment that can read a tiny amount of current. And that's just plain old finicky. So we're not going to do it for real as a lab, especially because we're remote. But even if we were in class, we would use an online simulation to see this photoelectric effect, to sort of see how nature really behaves, to figure out which model is correct. Is Planck correct and energy is related to wavelength, or is our old wave model correct and energy is related to amplitude? So what I would like you to do, the link is down a little bit lower. Here's the link. But you're going to open this simulation. What's going on in this one is light leaves a source from over here. So the light bulb's kind of like over here, and the light travels this way and hits a metal. The default, I think, when you turn it on, when you open this, is the metal's potassium, but later on in another lab we'll play with that. Light goes and hits that piece of potassium metal on the right and has enough energy to kick out electrons. So these little dots you see are electrons, and they're actually kicked out and moving back to the left. They're moving with some kinetic energy based on the energy of the light that hit it. In the simulation, we can program, that's what these buttons up here are. We can program this plate back here, this plate, to be a little bit negative. By making it a little bit negative, the electrons get kicked out of the plate and they start approaching that plate, but because the plate is charged negatively, at some point they'll be repelled away from that plate. And the bottom line is electrons with more energy will get closer to the negative plate. So this is a sort of way that we can eyeball how much energy the electrons have. So our simple experiment to see what's correct, if the wave model was correct, then changing the amplitude would give those electrons more energy. So to test if the wave model is correct, play with this. There's a typo, it's called brightness up here. Brightness is brightness, which is amplitude. Open the simulation, let her rip, and change the brightness. If the old wave model is correct, then changing the brightness will mean that electrons have more energy, which means they should get closer to the negative plate. So try that, and then reset it. If this new model is correct, then the energy is related to the frequency or the wavelength. In this one, we've got a wavelength slider or a wavelength arrows to change. It's an inverse relationship. The equation back up here, lambda was on the denominator. So since it's on a denominator, a smaller wavelength means a bigger energy. So when you get going with the lab, decrease the wavelength. And if Planck is correct, then a shorter wavelength should cause the electrons to get closer to the plate. So that's it for our first little lab. Go to that simulation, play with the wavelength, see what happens, play with the brightness and see what happens. Depending which one of these, so only one of these will happen. Either the wavelength will get them closer to that negative plate, or the brightness will get them closer to the negative plate. Test it, and then the answer to this first part of the lab is just tell me which one, based on that experiment, which one seems to be correct. Is the old wave model correct, or is Planck's new model correct? That's it for this part of the lab.